Once again, if we use the conservation of kinetic energy and the conservation of momentum equations, but solving them in a slightly different manner. The algebra is a bit more intense, not too bad, and it might be fun to try. The following equations result. We can find the final velocity of the first object. It's equal to m1 minus m2 over m1 plus m2 times the initial velocity of the first object, plus twice the mass of the second object, again over m1 plus m2 times the initial velocity of the second object. And I won't read the second equation, you can see it. But what's cool about this, look at the symmetry. Look at the denominators. They're all m1 plus m2. Okay, and look how we have the velocities here for v1 and v2, but we're basically switching the numerator. We have 2m1 there, 2m2 here, and here's m1 minus m2 here and m2 minus m1. Not sure what it means, but it kind of looks nice. So we're going to use these equations to make some other predictions about different collisions. In this case, where the mass does matter, it will change the result, unlike what we just went through, where the relative velocity expression was independent of the masses of the objects. We'll take three specific cases. We'll relate them to what we observe, and then we'll apply these equations to predict what happens after the collision. We'll have two equal mass particles colliding. We'll have a very heavy particle colliding with a light particle at rest, and then we'll have a light particle colliding with a heavy particle at rest. And here are the two equations that we're going to use. For a collision of two particles of the same mass, we can just replace m1 and m2 with m, because m1 is the same as m2. When we make the substitution over here, and go ahead and try that on your own, maybe you have a few minutes to do it now, they will simplify to v1 prime equals v2 and v2 prime equals v1. And that's shown down here in the picture. So what is that telling us? The particles exchange velocities. The final velocity of sphere 1 is equal to the initial velocity of sphere 2. Likewise, the final velocity of sphere 2 is equal to the initial velocity of sphere 1. You can look down here for the example. The objects both have same masses, and here's the velocity, the initial velocity of sphere 1. By the equation up here, that tells us that the final velocity of sphere 2 should be the same. So you can see how this arrow matches this arrow. And then sphere 1's final velocity, that's this sphere coming over here, will equal the initial velocity of the second one. So this arrow here, and instead of circling, I'll just kind of draw it there, they're equal. A nice example of that is playing billiards. When the cue ball hits a solid ball, the cue ball will stop, and the solid ball takes off with the cue ball's velocity. Now that's only true if we ignore friction and the rotational motion of the pool balls. In reality, you have to hit the cue ball a little below center. But we're not going to worry about that right now. It's just kind of a nice way to help you remember it. So the key phrase here is the particles, spheres, objects, whatever, they exchange velocities. Another good example is found in nuclear reactor engineering. When uranium-235 fissions, it releases 3 high-speed neutrons. The problem there is those neutrons are moving too fast to cause another uranium-235 nucleus to fission, so they have to be slowed down. They have to collide with something else that will slow down. We typically call that a moderator. What type of object would you use to slow down high-speed neutrons? If you have other objects that are of an equivalent mass to the neutron moving at a slower speed, when these high-speed neutrons contact that, they will exchange velocities, the neutron will slow down, and this other material or object will speed up. A hydrogen atom would be perfect. If you had a slow-moving hydrogen atom, the neutron would exchange velocities, it would slow down, and then the hydrogen atom would speed up, but you don't care about that. You don't need that for fission. Operational reactors use water for this purpose. Okay, water is heavier than hydrogen, right? It's 2 hydrogens and oxygen, but it's close enough, and it has many other practical benefits. Nuclear engineering is not just as simple as analyzing an elastic collision, but it's roughly the same concept here of slowing down the particles. A large mass striking a lighter mass at rest. Here's our large mass, here's our lighter mass at rest. So M1 is much greater than M2. That's what this double inequality sign means, much, much greater. So that means that M1 plus or minus M2 is just going to equal M1 approximately. So our equations, these very complex equations here, will simplify to V1 prime equals V1. So the heavier mass keeps moving with the same velocity, roughly. And the smaller mass, the very much smaller mass, takes off with twice the velocity of the larger mass. Let's just work through that, see how it goes here. Well, we know that V2 is equal to 0. There's V2. This is pretty easy. This whole term goes out. Now, since we know that M1 is much greater than M2, M1 minus M2 is going to be roughly M1. Same thing happens over here, and you get V1 prime is M1 over M1 times V1, which is just V1. So on your own, make this assumption, plug it into this equation, and see if you get that V2 prime is equal to 2V1. So for a large mass, mass 1, striking a smaller mass, mass 2, a much smaller, the first mass proceeds at basically its same velocity. It's a little smaller because momentum is conserved. It had to give up some of its momentum to the second object, but approximately it's the same velocity. The smaller mass object takes off with twice the initial velocity of the larger object. A good example is, for example, a bowling ball, which is very massive, striking a very light beach ball. The bowling ball will keep moving with the same velocity, approximately, and the beach ball will take off with twice the velocity of the bowling ball. And that's pictured down here, although this is a very tiny beach ball and this is a very large bowling ball. You can see the effect right here. One more example. We have a very small mass, M1, striking a very large mass, M2. So M1 is much, much less than M2. Here's our double inequality sign to show that it's very much smaller. And let's see what these equations simplify to. Again, I'll do the top one. You guys can do the bottom one at your convenience. So we have V2 is 0. Once again, this whole term goes out. Now, since M1 is much, much smaller, in this case, we get rid of this, we get rid of this, and we have negative M2 over plus M2, which just is negative 1. So V1 prime is equal to the negative V1. V2 prime 0, you can work out, you'll find that it basically doesn't move. Again, it has to move a little for conservation of momentum, but we're going to ignore that because the movement is so slight. The smaller particle rebounds with the same speed but the opposite direction, and the large particle basically doesn't move. A good example of that was if you were to hit a golf ball against a stationary bowling ball, or if you're hitting a tennis ball up against the wall for practice. That ball reverses its velocity but basically keeps the same speed, and the wall doesn't move.